Chapter 2, Exercise 17. Hints. Observe that all points in E have infinite decimal expansions, as the digit 0 is not allowed. Consider the set S of all sequences n equaling this, where each ni is either 4 or 7. Define a function f, this, by f of n equals supremum of this. In other words, f of n represents the real number with decimal expansion here. See section 122. Show that f is bijective and apply theorem 214 to show that E is uncountable. To prove the compactness of E, show that E equaling this, where S of k is the set of all sequences here, such that each ni is either 4 or 7, and j of this equals this. Compare this to the construction of the Cantor set, section 244. To prove that E is perfect, consider a point x in E with decimal expansion here, and another point y in E with decimal expansion here, where the digit mk is the complement of nk. That is, mk equals 4 if nk equals 7, and mk equals 7 if nk equals 4. Show that the distance between x and y is less than epsilon for a sufficiently large k. Solution. First, we expand upon the material on decimal expansions presented in section 122. Let x be in this. Then there exists a sequence n equals this of digits, that is, n of I, element of these, such that for every k greater than or equal to 1, we have this. We construct this sequence inductively. From the inequality here, it follows that this. Hence there exists a maximal integer n1 such that this, which implies this. Noting that n1 element of this, we obtain the following. Assuming that n1, n2, and so on to nk minus 1 have been constructed and satisfy this, we observe that the following. Thus, there exists a maximal integer nk such that this. Necessarily, nk element of this and this. In other words, this and thus that. Thus, the inductive construction can be continued. Let us note that for every x in this, and every integer k greater than or equal to 1, there is a unique sequence here of digits such that this. Indeed, assume that this and that are distinct sequences of digits of length k. Let j be the first index where nj does not equal mj. Without loss of generality, assume that nj less than mj. Then nj plus 1 less than or equal to mj, and thus the following. And the following. And the following. This implies that the inequalities here and here are inconsistent. In particular, we have shown that for every digit x in this, there is a unique sequence n equaling this of digits such that for every integer k greater than or equal to 1, this. The expression here is called the decimal expansion of x. Note that we have also proved the equality here, which will be used several times below. We note that the decimal expansion here of x in this cannot end with infinitely many digits ni equal to 9. Suppose, for the sake of contradiction, that there exists an index j greater than or equal to 1 such that nk equals 9 for all k greater than j. By construction, we have this. Thus, we have the following. Hence this. And by the Archimedean property and the inequality 10 to the power k greater than k, there exists a positive integer k such that this. From here, this, which further implies that this, hence this. On the other hand, since this, it follows that this, which is a contradiction. Conversely, let n equaling this be a sequence of digits not ending with infinitely many ni's equal to 9. We observe that each sum here is less than this for any kl. This is evident when k less than or equal to l. If l less than k, then it follows from the inequalities the following. The set here is bounded above by any number of the form here. Define x equaling supremum of this. Then, for every integer k greater than or equal to 1, we have x in between these. We now show that for any integer k greater than or equal to 1, the strict inequality x less than this holds. There exists an integer j greater than k such that nj less than 9. Otherwise, the sequence n equaling this would end with infinitely many digits equal to 9. Then we have the following. This establishes that for any sequence n equaling this of digits not ending with infinitely many ni's equal to 9, that there exists a number x in this such that x equals this. Denote by D the set of all sequences n equaling this of digits not ending many ni's equal to 9. Summarizing our previous considerations, for each x in this, there exists a unique sequence n element of D such that x equals this. This sequence is characterized by the inequalities below, inequalities 1, which hold for every integer k greater than or equal to 1. Conversely, for each sequence n in D, there exists a number x in this such that x equaling this. Thus we obtain a one-to-one mapping f of D onto here, defined by the property that f of n in this has the decimal expansion here. A function f, this, is given explicitly by f of n equals supremum this. Let E be the set of all x in here, whose decimal expansion contains only the digits 4 and 7. We note that E subset of this, denote by S the set of all sequences n equaling this, where each ni is either 4 or 7. The set S is uncountable. See the proof of Theorem 214. Define a function f, this, by f of n equals supremum this. The mapping f provides a one-to-one correspondence between S and E, implying that E is also uncountable. Next, for every n in S, by taking k equals 1 in inequalities 1, we have f of n this. In particular, this, which implies that 1 not in E bar. Consequently, the set E is not dense in here. Now let us prove that the set E is compact. For each integer k greater than or equal to 1, let Sk denote the set of all sequences here, where each ni is either 4 or 7. For every this in Sk, define the half-open interval I equaling this. For its closure, the closed interval j equaling this. Define the sets ak equaling this and ek equaling that. First note that each set ek is compact. Indeed, since each j of this is compact by Theorem 240, it follows that each j of this is bounded and closed, Theorem 241. Then ek is closed as a finite union of closed sets, by Theorem 224d. Also, Ek is bounded as a union of sets contained in this. By applying Theorem 241 again, we conclude that Ek is compact. Now, since each set Ek is compact, it suffices to show that E equals this. Indeed, the previous equality would imply that E is closed as an intersection of closed sets, Theorem 224b. It is also bounded since this. Thus, Theorem 241 would yield the compactness of E. Firstly, let us show that this. From the inclusion here, it is clear that this. To prove the converse, consider a point x element of this. Since x element of Ek plus 1, it follows that there exists a sequence this such that x in this. In other words, the following. It follows that all of this. Hence, x element of this. Since k greater than 1 was arbitrary, it follows that x element of this, which proves the equality here. Secondly, let us show that this. Indeed, let x element of E and let this be the decimal expansion of x. Then, for each k greater than or equal to 1, we have the inclusion below. Thus, x element of this. Finally, let us show that this. Let x element of this and let this be the decimal expansion of x. By the definition of sets Ak, for every integer k greater than or equal to 1, there exists a sequence this such that x in this. In other words, this. However, we also have the inequalities here. By the uniqueness proved above, we get the following. That is, all mi are either 4 or 7, which implies x in E. From the above considerations, it follows that E equals this, which shows that E is compact. It remains to prove that E is perfect. Let x in E, and let this be its decimal expansion. For a fixed epsilon greater than 0, let an integer k greater than or equal to 1 be such that this. Its existence follows from the Archimedean property. Consider digits mi equaling the following. Let m equal this and y equal that. Note that y doesn't equal x, as m doesn't equal n, and f is 1 to 1. Assume that nk equals 7, so that mk equals 4. We have the following inequalities. The following, and we continue. And we continue the following. Hence, we have this. The case nk equals 4, mk equals 7 is similar. X less than the following, and we continue. And we continue y less than the following. And this. In any case, a neighborhood here contains a point y in E distinct from x. Thus, every point of E is the limit point of E, showing that E is perfect. Here is a picture, sets E1, E2, E3, unions of black segments. A, B, C. Comments. In solving this exercise, we establish an important one-to-one correspondence between real numbers x in this and their decimal expansions here, where n equals this is a sequence of digits not ending with infinitely many ni's equal to 9. We had to exclude certain sequences of digits n equaling this to ensure the correspondence remained one-to-one. For example, consider the sequence n equaling this. The decimal expansion it produces coincides with the decimal expansion produced by the sequence m equals this. Indeed, for every integer k greater than or equal to 2, this. The supremum of these numbers is equal to 1/10, which corresponds to another decimal expansion here. The construction of decimal expansions we developed can be extended to any base b greater than or equal to 2 where b is an integer. Every real number x in this has a unique expansion here in base b in the following sense. Each ni element of this, not all ni are equal to b minus 1 starting from some index, and for every integer k greater than or equal to 1, this. Trivial examples of perfect subsets of R include the empty set, closed intervals here with a less than b, closed rays here, and the entire set R. This exercise provides a non-trivial example, the set E. Another non-trivial example is the Cantor set P, see section 244. Note the distinction between the sets E and P. The set E consists of numbers x and this whose only decimal expansion here is such that each digit ni is either 4 or 7. In contrast, the set P consists of all numbers x and this that have a ternary, that is base b equals 3, expansion here, where each ni is either 0 or 2. For example, 1 in P, since this is a ternary expansion of 1, though this is another valid ternary expansion of 1. Thanks for watching.